Okay, so let me start with a brief recap of what we're doing. So we're in a certain sense connecting four objects. We have a kind of a divergence-free and time-independent drift B in 2 dimensions, and which is random. So very loosely speaking, it's epsilon times the projection onto scales which are larger than 1 times the projection onto divergence-free of spatial white noise. So so that's the kind of ensemble of drifts, of random drifts we're considering. And based on this, we're interested in kind of the drift diffusion process, or rather its generator, which is given by B dot nabla plus Laplacian for the diffusion. And we were interested in the what you might call Lagrangian or average Lagrangian coordinates, the solution to the parabolic equation with initial data which are given by the identity. So that has an interpretation of the kind of averaged, with respect to the thermal noise, averaged position of the particle that undergoes drift and diffusion. But you can read it, what I'm doing is really about PDEs. So this is a PDE with a random coefficient. And on the other hand, and I will have to get back on this, we had kind of Brownian motion on the Lie group of trace-free 2x2 matrices. And there could be many Brownian motions. In fact, as many possible kind of inner products you can put on this 3-dimensional linear space. But there is one distinguished one, which I will come back to this time. So from this Brownian motion, we were looking at the corresponding process, diffusion process on the Lie group. So F is something that's Lie group valued, so 2x2 matrices of determinant 1. And the definition was that this was a 2-parameter object. There is kind of the initial time tau star, and then tau is the kind of active time, which is given by kind of taking this here as a driver in the sense of a Startonovich noise. This is for tau larger than tau star with the initial data which are given by the identity, the neutral element in this group for t less than t star. And the claim was that we can couple these two Gaussian objects so that there is kind of a tight relationship between this solution of a drift diffusion process and this diffusion on SL2. And that was the main statement. So there exists a coupling, and I will talk about it this time or next time around, of B and capital B, such that for all spatial points t and for all time horizons, if we look at the increment of the solution to the PDE, let's say anchored at the origin, and we compare it to this linear operator, and here I have to take the transposed, applied to t, applied to x, and we look at the at this expression, which means a little bit looks like almost looking at a Taylor remainder, and we average in time over the time horizon t, and we take the expectation with respect to the ensemble B and the F, then this is small in this in a specific sense. And now the most interesting thing is still to come, namely how to choose these two parameters. So there is a tau, the initial time in this sense here, depends on the distance of the length of the increment, or the distance between x and the origin. And the second parameter depends on this time horizon, capital T, and where tau of s was defined as a double logarithmic, iterated logarithmic expression, which I motivated at the very beginning, and which had this form here. So that was the main result. And last time I said that the interesting lesson to be learned out of this kind of coupling of relating kind of the solution of a PDE with a random coefficient to a diffusion on SL2 was that you learned something about the intermittency or intermittent behavior of the solution of this equation from kind of a very, not absolutely obvious, but very clear intermittent behavior of this object, which is a little bit like a stochastic exponential. And so that was already the second section about intermittency. And so there we had two results. One was a corollary from this one, and the other one was kind of the interesting intermittency result. So both require to work in the regime in a certain regime, which I will explain in a second. And in this regime, we could, in a certain sense, from the good knowledge of this object, we can say something about the increments. So we can say something about a modulus of continuity, spatial modulus of continuity of this solution. Namely, that this here was essentially behaving like the maximum of a ratio of lambda of t and lambda evaluated x squared, where lambda of s is defined as exactly this object. So square root of 1 plus epsilon over 2 logarithm 1 plus s. And so then we interpreted this here, and we saw that this was, in a certain sense, telling us that the kind of annealed spatial modulus of continuity of this, let's say, typical solution of this parabolic PDE is not quite Lipschitz, but by a logarithm, by power of a logarithm worse than Lipschitz. So you're kind of borderline Lipschitz. But then the interesting thing was that, so in the same regime, and for kind of exponents which are between 1 and infinity, if you take the pth power of this object here, then it doesn't scale like the pth power of this one here, but you get kind of intermittent behavior in the sense that you get this expression to power which is strictly larger than p, and there was a very definite answer, 1 plus 3/2 p minus 1. So which is strictly larger than p, sorry, if p is strictly larger than 1, but in a very quantified way. So in that sense, like in fluid dynamics, in a certain sense, in turbulence, the modulus of continuity which you detect from your solution depends on which moment you look at. It's kind of a moment-dependent function. And so the goal now of today, I started doing this last time. The goal now of today is to first continue the story of telling you how to fix this Brownian motion in such a way that you do get this connection, and how then from elementary properties of this object you see some intermittency, which should translate into proposition 1. So that was what we were in the middle of last time. So I first told you a bit about Stratonovich and Ito, and then we'll give you the definition of B. So, in a very, in a very loose and handshaking way, you may say that Stratonovich. So if I want to interpret this stochastic differential, this ordinary stochastic differential equation, in the sense of Stratonovich, which typically goes with this symbol circle, the way I should think about it is that this is the limit of smooth approximations of my driver, of my Brownian motion on the linear space. That's, I think sometimes that's called Wong-Sakai theorem. And as a consequence of this, Stratonovich, this way of writing the equation is good for the chain rule. And therefore, this is the reason why I started out with this, because since the chain rule is valid, from this form, you immediately learn that the fact that B lives in the Lie algebra means that F lives in the Lie group. So, so this is why putting Stratonovich here is natural. Then the other kind of cooking rule is that the Ito interpretation, or the Ito ID, can also be understood as a limit, but then it's the limit of forward or explicit Euler. And the advantage of this way, this approach to stochastic ODE is that this is good for taking expectations.
Can you pass on the hard revolution?
Yes, thank you. And last time I explained, or I gave a hint of the fact that, by the well-known Ito-Stratonovich correction, we learn that kind of this Stratonovich expression is equal to the Ito expression. So Stratonovich is equal to Ito if and only if my underlying Brownian motion, my Wiener process on this space, is not completely arbitrary, but satisfies the condition that if I look at it at time 1, that's a matrix, and I multiply this matrix with itself, and I take the expectation of this matrix product, which is again a matrix, then the expectation should be equal to 0. So that's the condition which ensures that Ito is equal to Stratonovich. And so which already puts one constraint on this object. And now let's put the second constraint on the object, which comes from the fact that, which is in certain sense related to the fact that this Ito form is not natural for the chain rule. In fact, if you want to use the chain rule, you need to kind of introduce what's called the Ito correction. So last time we had the Ito-Stratonovich correction. Now I'm talking about what's called the Ito correction. That's something related but different. And so, so let me introduce this. So if you have an observable, I think I typically call it zeta. So I want to speak about the kind of chain rule for Ito. So for df is equal to f dB. And chain rule for Ito tells you that if you look at an observable zeta, so some function on matrix space F, then kind of this object satisfies kind of a differential identity, which is kind of pretty much of the original form. You get kind of martingale term, which is given by this here, and which has, like, you know, that's the advantage of Ito, of the Ito form, has vanishing expectation. But then you get an Ito-Stratonovich correction, which involves the Hessian of the observable at the current state applied to the quadratic variation of f dB, the process which you get from f dB, and that's given by f tensor f, matrix component-wise matrix multiplied times the quadratic variation of B, which, because B has independent increments, is a Brownian motion, we know well. And now you apply this to the observable, which is given by the squared Frobenius norm of the matrix with a factor 1/2. So that's, you can write as the trace of the adjoint of f times f. And if you do that, you find that this expression here, which is just the covariance, which leads to the covariance of B at time tau equal to 1, takes a kind of simple form. So in this case, you get that this is the trace of f star f multiplied with the matrix, which you get from taking the expectation of B at time tau equal to 1, B transposed at time tau equal to 1. And now you see that there is kind of a second natural postulate, namely, hence you get kind of a nice evolution equation for the expectation of the Frobenius norm, namely that that this is just kind of solving an exponential equation, namely that this is equal to the expectation of the Frobenius norm itself, the square of the Frobenius d tau, if and only if you get a second condition of the type we had up there, namely you want that the expectation of B at tau equal to 1 and the matrix product with the transpose this time, that this is equal to the identity. So now you have these two conditions, and then you use a little bit of representation theory for the abelian group SO2 to infer the following. Let me erase this. So that's a kind of slightly modified version of a lemma which I gave in the first lecture. So there exists a unique Brownian motion on on the Lie algebra SL2 on this three-dimensional linear matrix space with the following three properties. It's SO2 invariant, meaning that for all matrices in SOQ, in SO2, Q minus 1, B, Q has the same law as B. And it satisfies exactly these two conditions. The expectation of B tau times B tau is equal to 0, and the expectation of B tau times B tau transposed is tau times the identity. So that's the that's kind of, if you want, we didn't find it in the literature, but I wouldn't be surprised if this is something which is well known to people in in stochastic processes. And so that, in a certain sense, now defines the object I'm talking about here, and therefore also defines this nonlinear process on the Lie group SL2 by either Ito-Stratonovich integration. Since
is this only two-dimensional, or?
no, this part. So what is two-dimensional comes in a second. So I mean, we did it in the two-dimensional case because then the representation theory gets easier. But I'm pretty sure that this holds in any dimension. What is two-dimensional, and there we don't know how important the two dimensions are, is what follows now. And that's the connection to a kind of a stochastic exponential. And therefore intermittency, if you want, for f. So let me explain this. So let's again consider this Frobenius norm. With a convenient factor of 1/2, which is made so that if I plug in the identity, it's equal to 1 because I'm two space dimensions. So this is always, in fact, at least 1 on the Lie group. And in fact, it satisfies, and that's which is specific to two dimensions. It satisfies in d is equal to 2 its own Ito evolution. Meaning I can, at least in law, recover it by the following one-dimensional Ito equation, where here I have to put r square minus 1 square root dw, where the small case w is a 1D Brownian motion. And of course, it has the initial data. Since I'm starting in the identity, at least that's what I'm doing here, it has the initial data equal to 1. That's specific. That's, in a certain sense, a little bit an algebraic miracle that you find this here. It's perhaps reminiscent of Bessel processes. When you take kind of a 3D Brownian motion, the distance to the origin, or its square, which is also kind of a square one-dimensional expression, satisfies its own process. And so that's what we find here. And now from this one, you get, in a certain sense, you learn intermittent behavior because you can introduce a very closely related quantity. So consider R tilde to be the largest eigenvalue of f adjoint f. So if you want the square of the largest singular value of f, then of course, because the matrices have determinant 1, R and R tilde are closely related. So R can be written as 1/2 of R tilde plus 1 over R tilde. And in fact, that's the crucial point. The R tilde can be easily related to a stochastic exponential. So an easy argument, easy comparison argument on the Stratonovich level shows you that not only is 2R larger than R tilde, which is immediate from this, but R tilde is larger than S, where S is a stochastic exponential. The stochastic exponential, which is given by almost the same type of equation where here you put in the large scale behavior. And that, of course, has an explicit solution, and this is why it's called stochastic exponential. Namely, S is equal to E 1/2 tau. The 1/2 comes when you pass from Ito to Stratonovich. Stratonovich is easier for explicit solutions, and then you get plus this Brownian motion. And from this explicit form, you can read off essentially the intermittency, or let me say non-equi-integrability, which of course is a very well known phenomenon. Namely, that the median of this random variable is a power of the mean, so the expectation of this random variable, and the power is exactly 3/2, and kind of this mean can be easily derived from this Ito form is equal to E tau. So in other words, that kind of the fact that the for large taus, the median is much, much larger than the mean, which means, at any given tau, the distribution function of this object, in a certain sense, is very bimodal. It puts a large kind of half of its mass comes from extremely large values, whereas in a pathwise sense, it behaves in a much more moderate way. The pathwise behavior, in a certain sense, is dominated by this, because by the law of iterated logarithm, this here grows a bit more than the root. But the mean is much larger, and so in a certain sense, this behavior has to come from the fact that the median is even much larger, and it's exactly this exponent 3/2, which comes up in the result on the PDE solution which I wrote down. So that's the exponent which governs the intermittency. So in a certain sense, I think we kind of related this interesting intermittent behavior on the level of PDE with random coefficients to kind of a very obvious intermittent behavior on the level of a very standard stochastic process. So I think that's perhaps in a certain sense conceptually the merit of what we're doing, and in a certain sense we would like to connect these two objects in a stronger way than we do presently, to even say kind of make stronger statements, also addressing the entire path behavior than what we do now. So in a certain sense, our theorem, which I wrote down here, which is still here, which connects the two sides, is, as it's stated, limited by what we do on the level of homogenization theory. And that's what I want to do now, explain to you in a certain sense what is behind, what drives or what makes this connection, which I find, not that obvious at the first place between this PDE, which in a certain sense governs the Lagrangian coordinates of the underlying stochastic process in time, and this seemingly unrelated process on the Lie group of volume-preserving endomorphisms. So that's the next section I want to tackle. Other questions? Doesn't seem to be the case. So let me tell you how to make the connection between this simple object and this more complicated one.
One question is,
Yeah?
until the gradient equal to S, that's something that you just told us about.
Yeah. So it's not difficult to see. In fact, it's just a couple of lines. What you do is you you view r tilde as a function of r defined by this identity. Then you use Ito-Stratonovich calculus to write down the SDE that defines the evolution of r tilde. And when you do this, you see that you get something which looks like this, but now with a drift term that's different. So in a certain sense, this change of variables kind of made the sigma identical, but now puts the difference in the drift term. But on the level of the drift term, there is a clear monotonicity. So the drift which you get for r tilde pushes you even more strongly to large values than this one.
And the
Initial starting point is always the same. I'm always starting at 1. I'm always starting at 1. Okay, so but it's really kind of an easy, nothing easy comparison argument. Okay, so let me start with the next chapter. So that would be on kind of what we called incremental or scale by scale homogenization. And this will teach us, in a certain sense, or this will inform us on how to couple these two things, these two objects. So that will tell us how the coupling between B, how the two worlds connect. So, so let me start what I'm going to erase. Perhaps I'm going to start again here. So I start with something, namely by introducing kind of a large scale or infrared cutoff, which in a certain sense is artificial, but which will play the role eventually of a dynamic variable. And so therefore it's important, and speak a bit about homogenization. So, so let us write our solution of the parabolic equation, this Lagrangian, if you want, averaged noise, thermal noise averaged Lagrangian coordinates as a perturbation of the identity. So let's introduce the phi by this identity, and then an easy calculation shows that I'm always getting wrong, confused with the sign here because I'm using the negative convention for the generator. Then the advantage of this is you have kind of vanishing initial data, but the price to pay is that you have a right-hand side. But another advantage of this is that as B, phi, this kind of perturbation, in a certain sense, this displacement is centered, so it has zero expectation, and stationary. So stationary means its law is shift invariant in space. And now first important thing to realize is that, and this is in a certain sense a side effect of what we're doing, you cannot let the limit t go to infinity in this equation. You don't recover a solution of the limiting elliptic problem by letting t go to infinity. However, it exists if you introduce a large-scale cutoff for B. So if you replace B by BL, and it's convenient to introduce the BL again just by plain Fourier projection. So the Fourier transform of BL at some wave number k is just given by the Fourier transform of B at some wave number k. Those are distributions, but then I'm just looking at kind of wave numbers which are not too large, which are less than 1 over L. So L has dimensions of the length because k is, has inverse lengths. So this is kind of a large-scale cutoff. So now in a certain sense, in frequency space, we're operating between 1, which was kind of the large wave number, small-scale cutoff, and 1 over L. So that's our active band in Fourier space. And so if we replace B by this kind of cutoff object, then the limit exists and satisfies script L, subscript L, because that involves the B, the cutoff B, phi L is equal to BL. And in fact, it's also unique if you insist on the fact that its gradient is stationary and centered. And in fact, this is a well-known object. It's sometimes called the corrector for this kind of heterogeneous or random drift diffusion operator. And so from a point of view stochastic analysis, having the corrector is interesting because it gives rise to the harmonic coordinates for the process. Yes, thank you. So this if the minus is there, then it should also be here. And this here is defined with the plus. All right, thanks. So that gives rise to what is called harmonic coordinates. Let's call them UL, and that just reverses what I did here. So now I define UL of x as x plus phi L of x. And those are good coordinates for the process we started with, but now with this kind of cutoff drift. In fact, but that's not important for now. In these coordinates, this process turns into a martingale. That's kind of a probabilistic way of saying, what the merit of solving this equation is. And since our drift, even if I do this cutoff, is divergence-free, these coordinates, in fact, satisfy kind of also another equation, or I can rewrite the equation which is satisfied by phi L, respectively UL. I can rewrite this as kind of a divergence form equation. UL, let's look at the coordinate, at the ith coordinates, ULI BL is equal to 0. So, and then homogenization theory tells you that this, you can learn something from this flux or current, namely that the effective diffusivity which I alluded to in the first class, that the effective diffusivity lambda Li in direction of EI can be recovered from taking the expectation of this object, which is stationary, So it doesn't matter at which point I'm evaluating this object. And this gives rise to the effective diffusivity in direction EI. And since we have isotropy, this diffusivity doesn't depend, in fact, on which direction I'm looking at. And I can again recover it by the Frobenius norm of the gradient of the full object squared with a factor 1/2. And homogenization theory then tells you that this operator here, this heterogeneous operator, or rather its resolvent or its inverse, is well approximated by a homogeneous operator, namely the Laplacian with a prefactor which is given by the effective diffusivity, at least on, on large-scale objects. So that's kind of a very quick way of putting some homogenization theory into this business, which works, provided you introduce this cutoff. But of course, now we want to get rid of this cutoff. This cutoff is artificial. I mean, this was just there to be able to use more or less standard theory, which I'm kind of reporting here very quickly on these two blackboards. And so in a certain sense, we want to let L tend to infinity. But the best way to do that is not in kind of brute force, but to do it in an incremental way. And that's kind of perhaps the main idea here. So that's incremental homogenization. And the definition of a proxy corrector, which in fact is defined by an Edo, which interestingly is defined by an Edo differential equation where the cutoff length L plays the role of the dynamic of the time variable. So let me explain this. So the idea is to apply the derivative with respect to this cutoff scale to the defining equation for phi L, which now let me spell it out. Is this equation. So if you do that by Leibniz rule, what you get is minus your kind of cutoff generator applied to the increment to the derivative, and I'm using, because eventually this will turn into Ito calculus, I'm using the symbolic differential equation, is equal to two terms. One term which comes just from applying this to the right-hand side, and one term which comes when the derivative falls onto B. And now we do two kind of a priori completely uncontrolled approximations, but which turn out to work. We homogenize, which means we use exactly this inside. So we replace the inverse of this operator by the inverse of this operator. And then, in a certain sense, we take the leading order term in epsilon, or we linearize, which means on this right-hand side, we neglect this term. So what we end up with is the equation minus lambda L Laplacian is equal to a Laplacian of d phi is equal to dB. And let's be a bit more careful. Let's even, because we don't know this quantity, let's replace it also by proxy phi tilde to be chosen self-consistently. So let's make this ansatz. Now this has the advantage that the resulting field phi is not only centered stationary, it's even Gaussian. So that is even, that's in a certain sense the merit of dropping this term, that you preserve Gaussianity. You don't get into kind of higher chaoses. But it's not good enough, because in order to kind of in the end do something self-consistent, so connect the lambda tilde to the lambda, we have to be interested in gradients. And this type of very loose homogenization result is not good enough on the level of gradients. But there is a well-known kind of correction which you have to do. So and the correction goes under the name of two-scale expansion. So if you're interested in approximating the gradient of a solution with this variable coefficient operator, then it's not enough to take the gradient of this object, but you have to kind of hit it with kind of what is called the two-scale expansion, which with Einstein's summation convention means you apply this operator, which is a differential operator, to the solution of the homogenized problem which you got, and then you're allowed to take the gradient. So this is something which is very well appreciated in any type of homogenization, periodic, stochastic, and goes by the name of two-scale expansion, because typically people would put small parameters, and then this is kind of the first order correction, which you need even for the leading order of the gradient. And now this motivates the definition of the proxy corrector. So you take whatever comes out from here, that defines in a certain sense a driver. And then you define the proxy corrector, phi tilde L, via an Ito evolution. And the Ito evolution just is informed by or uses this two-scale expansion. So what you do is, I'm writing down a differential equation in L, in what we introduced at first just as a benign kind of cutoff parameter in the length scale. We now use it as a dynamic variable, as I keep repeating. And now I'm not taking this definition, but I'm taking this object and I kind of post-process it by the two-scale expansion. And here, since I don't know this object, the only choice which I have is to put a tilde in here and use the kind of initial data, same initial data, that this is equal to 0 at the starting length scale, which is equal to L1. And so again, this is kind of a field-valued stochastic differential equation in this time parameter L. And that's the driver. And this product here has to be interpreted in the sense of Ito. So that's the definition. That's the definition of a proxy corrector. And now, surprisingly, despite these strong approximations and this kind of strange use of a cutoff scale as kind of dynamic parameter, this works, and that was essentially what we proved in this a couple of years ago. So returning to the u, now on the level of the tilde and the L. So this is again x plus phi L tilde of x. Returning to this object, we have the theorem 2. So that's from the older work with Peter Morphy, Georgiana Schatzi-Georgi, Peter Morphy, and Lihan Wang. And it just got accepted by analysis of probability. So provided we relate the time horizon to the cutoff length scale in the usual parabolic way, and we choose this lambda L tilde, which was still a free parameter to be chosen in self-consistent way. Now comes the self-consistent choice. So if we choose this as the lambda of L squared minus 1, lambda being defined in one of the, in kind of the first corollary. So let me remind you what this is. So that's the expression 1 plus epsilon square logarithm of L square root. So if we link the time horizon to the spatial cutoff in this parabolic way, and if we define our proxy effective diffusivity in the way I try to motivate heuristically in the very beginning, then we get kind of an error estimate. So if we look at the gradient of u, for instance, the origin, but any point will do, and we compare it to the gradient of UL tilde, and we look at as usual, at the time average, and we take the second stochastic moments, then this is less than epsilon squared times lambda t. And so that's really what makes everything work, which kind of connects a dynamical point of view to the PD via these kind of somewhat bold approximations, which, however, turn out to. And do I still have the time to explain one blackboard for the coupling? Okay, so now this in a certain sense tells us how we should couple. So let's recall what we have. So we define the driver or its increment d phi by solving the Laplace equation with diffusivity, which is given by this expression. And on the right-hand side, we have the increment of our white noise in the kind of Fourier cutoff. And hitting, where is it? Hitting this top equation with the gradient and passing from phi tilde to u tilde, we note that d gradient u tilde of L is equal to gradient u tilde plus phi L tilde I di times gradient d phi, and if you want initial data given by the identity matrix. And now what I hope you still can see is that this here exactly is, if for a moment I neglect this term, the type of equations we were looking at on the level of the diffusion, right? We have a driver here. Now this is still a field, but if I restrict it to a point, then this is kind of a matrix value driver, and we have this multiplicative Ito form of an equation which tells us how this thing evolves. And so that from this we can read off the coupling we need. So the coupling we need is that the BL on the side of the Lie algebra SL2 is related to the B cut off, let's say, evaluated at the origin after we apply to it the inverse Laplacian, and we normalize it in this way. So if I define the B, it's easy to see that 0 infinity, this is an SO2 invariant Brownian motion on SL2, which is independent of epsilon. And then we need a change of time scale or dynamic scale, which gives rise to the tau, which we have in the definition of B. So as a change of time scale. So that's the explicit definition of the coupling. So we get it from kind of cutoff in Fourier space and adding, you know, in a certain sense, infinitesimal annuli to our random drift after, I think I've got the gradient, after, you know, manipulating it in Fourier space or in real space by these differential operators. So that's in a certain sense what one can read off. So that's the I think that's the main conceptual part. So anyway, my time's over. So I still have one hour left. So I guess in this 1 hour, I would like to speak a bit about the ideas behind this homogenization result, because again, this is non-standard. We prove it dynamically. So not like homogenization results are typically proved, because anyway, it's borderline homogenization. So in a certain sense, we also proved this homogenization result by Ito calculus, and so in a rather unusual way. Okay, so thanks for your attention.
So I'm curious about this coupling of little b and capital B, like how you came up with it basically. So did you have the like red circle formula first, and then kind of realized it kind of looks like you have this SL2 value diffusion?
Exactly.
Okay, so that came first.
So what came first is kind of a discrete version in L of this formula. So this paper here was done in discrete increments, and then we realized that things were, you know, proofs were getting, this was easier to prove in a continuum case. And then we started thinking about, about the special structure of this equation, and realized eventually that this is, you know, should be interpreted as a diffusion on this Lie group.